Let's now find a confidence interval for one proportion using the information that we have just learned. This study is based on 1,000 adults in the UK, 41% of whom say that they start in the fetal position when they sleep. We'll find a 90% confidence interval for this proportion among all adults in the UK. So first of all, we're given that p hat is 0.41, and n is the size of the sample, which is 1,000. We'll check that conditions are met for using a normal distribution. This is going back to the exploration we did where we said that really we need to see that the counts, both what we're counting and what we're not counting, are at least 10. So in this case, what we are counting is 41% of 1,000, and that we get by n times p hat. So this calculation is going to be 1,000 times 0.41, which comes out to be 410. Now for what we're not counting, there's always an easier way and a harder way to do it. We know that we have 1,000 people total. 410 claim that they sleep in the fetal position, so we know that the remaining 590 answered otherwise. So I can do this the easy way since I know the total, but if I wanted to do this calculation n times 1 minus p hat, that would come out to be 1,000 times 1 minus 0.41, which is 0.59. So don't think that you always need to use these exact formulas when you're checking conditions. It's really about the counts in the group that you are counting and the counts in the group that you are not counting that we want to both be at least 10. Here we can clearly answer yes because both of these are much greater than 10. Z star for a 90% confidence interval, we need to back up and look at that summary table. And for 90%, it looks like we've got 1.645, so we just write that one down. That's just a table lookup. No calculations at all in finding that Z star. Now the point of that Z star is that it takes the place of the 2 that we got used to back in chapter 3. We are now saying that the margin of error, instead of being 2 times the standard error, it's Z star times the standard error, where Z star is usually pretty close to 2, but it varies according to the confidence level. So in this case, we've got 1.645 as our Z star, and we're multiplying that by the standard error estimate that we are given, 0.0156. So I'm going to bring in a calculator, and I get 0.025662, which I can round off. Since my proportion is given to 2 decimal places, I find that it is most meaningful to take the margin of error either to the same number of decimal places or just 1 decimal place further, depending on how large or small it is. I'm going to go ahead and take it to 1 decimal place further, and of course I have to round this 5 up to a 6 because the next digit is greater than 5. So I'm going to say that margin of error is 0.026. So that for my final confidence interval, I will start with my p hat of 0.41 and add and subtract the margin of error of 0.026 to get the 2 endpoints. For 0.41 minus 0.026, I get 0.384. And for 0.41 plus 0.026, I get 0.436. So that my interval starts at 0.384 and goes up to 0.436. Now we're going to take this one step further and introduce a formula for the standard error. one of the benefits of using theoretical distributions is that there are formulas for these things. We don't have to rely on something like a bootstrap or a randomization distribution to get us an estimate. We can just calculate it based on our sample statistics. So for a confidence interval, we use this formula where we take our sample proportion p hat and our sample size n and plug it all in here. So let's see what we get using the values for this example. Our standard error in this case is going to be a big square root around the whole thing. Get used to drawing that square root nice and tall so that you remember it applies to the denominator as well. 0.41 is our sample statistic, and 1 minus 0.41 is 0.59. It's easier if you do this part separately and don't put the whole 1 minus 0.41 in parentheses. It's going to be easier to enter into our calculator if we just do that as a side computation. Our n is 1,000, so I'm going to put 1,000 in the denominator. And now we're at the point where we're ready to put this whole thing into a calculator. The type of calculator that I'm using here is really modeling the one-line display, which is the less straightforward kind of calculator to use. So if you have a better calculator, you might be able to do this in a way that's more clear. I'll just show the more difficult type. I would need to really follow order of operations here and start entering the numbers and operations from the inside, kind of following order of operations, and work my way out. So I'm going to start in the middle with 0.41 times 0.59, and then I'll evaluate that. Now I say divided by 1,000, and again equals, so that I have the whole inside of the square root. This type of calculator, when I hit the square root button, it takes the square root of whatever is showing on the screen. So some types of calculators you could start by entering the square root button and you would then enter the expression. Here I'm going to hit this square root button to get 0.015553. I'll go ahead and write that down. And I'm asked to round this to 4 decimal places. That's a pretty good rule of thumb. I would say at least 4 is a good rule of thumb. Because this is not our final computation, we really want to take it out to more decimal places than it seems like we should need. Otherwise, our final answer might have more rounding error than we anticipated. So to 4 decimal places, that means I'm going to keep really just up to here, but again, since my next digit is a 5, I'm going to round this one up to 6 so that I get a standard error estimate of 0.0156, and I can check to see if that is consistent with what we were given above. Sure enough, right here, standard error is 0.0156, so we now know where that number came from. And we can answer yes. Most of the calculation errors that occur when someone knows the formula and is plugging in the right numbers have to do with not taking the standard error out to enough decimal places. So while you're working on your Wiley Plus homework, if you feel like your computations should be right and you keep getting told that they're not, they might just be off by a little bit more than the tolerance that's built into Wiley Plus. The first thing I would look at is how many decimal places you're taking your standard error to. 4 decimal places is generally sufficient, but if something goes wrong, it doesn't hurt to take it out to 6. If you have lots and lots of leading zeros, that would be a situation where I would consider taking it out just a little bit further so that you have several non-zero digits, not just several digits total.